This is a talk on near-field wireless communications by Hans, and I'm going to let John Sandorum, who's our AESS chairman now, actually do the introduction for Hans. But I just want to give, as the vice chair for AESS and a Dynetics employee, I want to thank Dynetics for the room and introduce myself as AESS vice chair. My name is Philip Henson, and I want to say thanks for you guys coming out. And I'm going to let John introduce Hans for you.
All right, thank you, Philip. As Philip said, I am the chair for the local AESS Huntsville section, and this is our first meeting of the year, so thank you all for coming. This is actually a joint meeting with the JCAM, Joint Communications and Antenna.
And Microwave
Society. So we're especially pleased to have a 2-for-1 deal here of meetings. And it's my pleasure here to introduce Hans, who is the CTO of Q-Track Wireless Corporation here in town. Hans has earned degrees in engineering and physics from Purdue University and a PhD in theoretical physics from the University of Texas. He's had a variety of work experience across the country at Lawrence Livermore, Electro Science Laboratory, and also here in town with the Time Domain Corporation before being the author of The Art and Science of Ultra-Wideband Antennas. So I think that we have a very interesting talk in store for us here today, and without further ado, I'll hand the floor over to Hans.
Well, thank you for that kind introduction and for the opportunity to speak here today. This is actually effectively a test run of a presentation I'm going to be giving at the 2014 IEEE RFID conference next week. I appreciate this opportunity to share the results with you and get your feedback. I encourage you, if you have any questions, please speak up. I'll be happy to tailor the talk to your individual interests. What I'm going to do is break it up into 2 pieces. The first half of the talk, I'm going to speak about some of the history and the origins of near-field wireless. I'll provide a survey of some applications and some of the basic properties of near-field electromagnetics. The second part of the talk is a little more theoretical. I'll get into the link budget associated with near-field wireless links, talk about electrically small antennas, and how to calculate field and some of the regulatory limits that are associated with these kinds of systems. Now, near-field wireless actually predates far-field wireless. The original near-field, well, the original wireless systems were used to provide railway telegraphy. But a lot of the original near-field systems were forgotten because of the superior performance and characteristics of far-field wireless. I'll talk about why they were forgotten and a little bit about the rediscovery of near-field wireless. Now, to begin with, long ago, 1870s, people identified the need to send messages to and from moving trains, to coordinate trains, avoid collisions, and possibly to send messages from passengers on board the train to stations. Original techniques for addressing that involved mechanical linkages to conductors, like sending messages along the tracks themselves. Well, that didn't work very well. So in the 1880s, a variety of investigators started taking a look at how you might be able to inductively couple telegraph signals between moving trains and wires or infrastructure around the track. And these are some of the systems that they investigated. Similarly, with the explosion of application of electric motors, inventors discovered or invented ways to try to couple wireless energy inductively between an infrastructure along the track and electric railroad cars themselves. So a lot of the inductive wireless energy or power transfer concepts that are in vogue today actually date back to the 1880s, the 1890s. The first commercially successful system was actually pioneered by Thomas Edison and some of his collaborators. What they did was investigate ways to inductively couple between either overhead wires or wires in a track. I found a nice depiction of one of their systems showing how a wire or cable was embedded in the railroad track. Inductive pickup coils underneath a train car would pick up the signals, and then an operator on board the train could send telegraph signals to and from the train to adjacent stations. The system worked well and was deployed for a period of several months. In fact, it was instrumental in sending rescue to a train when it was stranded by a blizzard. But apparently the business people of the 1880s and 1890s were not as dedicated towards staying in constant contact with their offices as we all are today, and the system ultimately was not economically successful. Well, undeterred, Edison looked at alternate ways of sending wireless. In the early 1890s, he explored an electrostatic way of communicating between ships and shore stations. It's an application that was very important for Marconi in his early days. And in the UK, the head of, or chief engineer for the British Post Office, which was also responsible for all telegraphy in the UK, William Henry Preece, did a bunch of experiments on inductive wireless signaling. The experiment he set up involved an antenna a mile in circumference, a quarter mile on a side, and the two antennas then were separated by about a quarter mile. Now, obviously, it's kind of tough to find a lot of practical applications for wireless links where the antennas are comparable in size to the distance you want to communicate across. But improving the technology, he was able to set up a demonstration system that could communicate a respectable distance of several miles across the British Channel. Ultimately, these and other efforts toward near-field inductive or capacitive communication were overshadowed by contemporary developments. Now, you can't mention wireless power transfer without bringing up Nikola Tesla, because he explored virtually every technique you could think of for sending energy wirelessly. He did high voltage, high frequency systems, like in some of the dramatic pictures you have of his Colorado Springs experiment, where he's sitting there reading a book calmly on a long duration exposure from sparks that are illuminating his laboratory. He did inductive power transfer techniques. Ultimately, he wanted to create a vast tower, and there's an artist's depiction of it there at Wardenclyffe on Long Island, where he would actually charge up energy into the ionosphere and make it freely available all over the globe. And J.P. Morgan funded him initially, but I think had difficulty getting over the freely available part of that, and ultimately in World War I, the tower was torn down. Well, in the late 1880s, early 1890s, Heinrich Hertz discovered and experimentally validated the existence of far-field wireless, of electromagnetic waves. And Hertz and his successors ended up pretty much overshadowing these early near-field or inductive techniques. One of the key persons in this was Oliver Lodge. Lodge invented the biconical antenna and the bow tie antenna, for instance, and he also came up with the concept of tuning to a particular frequency to send communications, which is a fundamental part of wireless even today. Now, Marconi really commercialized the approach and invented a lot of antennas that, working with long frequency or low frequency, long wavelength signals, you can recognize as being important electrically small antennas today. Fan and conical monopoles, and effectively patch or L-type antennas, only on a much larger scale to cope with the lower frequencies that he was employing. Now, by the 1930s, or up to and into the 1930s, the theoretical basis of electromagnetics from Maxwell's equations was still not widely applied in radio engineering. A very practical, successful radio engineer could be designing radio links and not have to have a detailed knowledge of Maxwell's equations, as witness Frederick Terman here writing in his book, Radio Engineering, which was the leading textbook on the subject in the 1930s. Sergei Shelkinov, who's largely responsible for introducing practical theoretical techniques into RF and electrical engineering, noted in 1970 that back in the 1930s, Maxwell and Maxwell's equations were totally alien to a lot of the engineers of the period. Well, you can look at a frequency chart from this one from a book published in 1930 to see what was going on and where the frontiers of radio science were. The frequencies are on the right-hand side there in kilocycles. So what you see is past 30,000 kilocycles, or 30 megahertz, the RF spectrum is completely experimental and amateur use only. That would change in the 1930s and certainly into the 1940s with the discovery of VHF and UHF signals and microwaves. So at this critical period when Maxwell's equations were starting to come into RF engineering, the applications of interest were all relatively short wavelength signals, and the fine details of what might be happening within a quarter or a half wavelength of an antenna really weren't of practical significance in the wake of all of these much higher frequency, shorter wavelength, longer range type systems. Even today, when people talk about electrically small antennas, they're often thinking in terms of antennas that are still on the order of maybe a tenth of a wavelength, not that much smaller than a quarter wavelength itself. So we've discussed some of the origins and history of near-field wireless. I want to go on to survey some of the applications that are involved. Now, the key thing to keep in mind is that high frequency and far field wireless works great if you want to send signals a long range in a near line of sight kind of link, if you want to have a large bandwidth or a very high data rate. That's what high frequency wireless works very well for. But near field wireless and near field links have their place too. They work very well if you are content with a relatively modest data rate. If you are willing to accept a relatively short range, going out to maybe a quarter or a half wavelength of a relatively low frequency. And where they really shine is their performance in complicated, cluttered environments. They're robust with respect to blockage and multipath. Taking advantage of those applications are a wide variety of applications. A few years ago, some folks at MIT did a demonstration showing how they could inductively power a light bulb at a relatively short range. They were operating at 9 megahertz in their demonstration, and they've since formed a company called Witricity to exploit that. There are a number of other companies pursuing various kinds of short-range wireless power transfer, including Y-Power. PowerMat Technologies sells an inductively coupled mat, and you can either get a phone with an inductive coupler built in or a little dongle to plug in, so you can set your phone down on a mat and charge it up without needing to plug in a power cord. And there's another company, Key, that is offering wireless or an alliance for wireless power charging standards. Near-field magnetic induction has been used for almost 20 years now in wireless headsets. The idea is to use a HF RF signal on the order of 10 to 15 megahertz to create a short-range near-field link between, say, a handset and an earpiece or a handheld mic, where you can take advantage of the short range, in this case about 2-meter range of the wireless link, to have a very small, confined, private link between your mic or your headset and your handheld that just by virtue of the way near fields work, you're not going to be able to physically detect or pick up at any significant distance. This approach was pioneered by a company called Oricom that was acquired by Freelink in 2007, and Freelink sells a variety of headset and products typically for police and security applications that employ this. Now, about 10 years ago, a number of companies joined together to form the Near-Field Communications Forum. The idea here is to use 13.56 megahertz signals to provide a very short range on the order of maybe 10 centimeters or less data link that is used for security, for contactless payments, or for identification of phones. And again, one of the advantages is that by virtue of the physics of the signals, they're pretty much indetectable if you go much beyond that 10-centimeter range, which provides an additional physical layer of security to the RF signaling. There are a number of location systems that have been devised that exploit these type techniques. Two companies, Polhemus and Ascension, use either low-frequency AC or pulsed DC to create very precise location and orientation type systems that are used for applications from figuring out where a pilot's head is so that you can align a heads-up display with where he is in the cockpit and where he's looking. It's even used now, some recent applications are for guiding surgical probes to upwards of a millimeter precision. So there's some very interesting things you can do with these signals. Now, my personal interest in near-field wireless comes from a technique called Near-Field Electromagnetic Ranging that I co-invented with my QTrack colleague, Bob DePere, about 10 years ago. This allows, at a range of about 20 to 60 meters, you to provide about 30 centimeter to a meter accurate location tracking, even in a complicated indoor propagation environment. Our current systems are tracking on the order of about 80 tags with a 1 hertz update rate. Another company that uses low frequency for active RFID is RuBee, which uses, or actually it's visible assets, and they call the technology RuBee. There's a standard IEEE 1902.1 that describes how this works. They can send about 1,200 baud data on their link with a relatively short range of 15 meters. But again, because of the low frequencies, it's very penetrating, very robust in a complicated environment. And finally, there are a host of radio frequency identification, or RFID, techniques that operate either around 120 to 150 kilohertz, so-called low-frequency RFID. A lot of the contactless badges that you'll see for security access use this kind of technology. And there's HF RFID that operates around 13.56 megahertz with a little longer range that's used in a lot of inventory control type applications. So all those applications take advantage of these properties of near-field links. They work well if you can live with modest data rates at short ranges and really need a link that works well in a cluttered, blocked environment where otherwise you might have a lot of multipath. Well, now I want to talk a little bit about some basics of near-field physics and what is the near field. There's a really great article that Charles Capps wrote back in 2001 that was published in EDN. Well, let me go back to this, where he went into detail about all the many definitions of the near field. He commented that he had sat down with a couple of engineers and had about twice as many definitions of near field as he had engineers he asked the question to. So the typical definition that we use in near-field wireless is the radian sphere, the wavelength over 2 pi distance where the near field and the far field are equal in magnitude. That's a typical boundary for what we would regard as being the near field. But other people will look at a large antenna and ask, when do the signals coming from it become a plane wave using that 2D squared over lambda criterion? A lot of EMC engineers will take 5 times the radian sphere and mark that as the distance at which the field impedance converges to 376 or 377 ohms, which is characteristic of far field signals. And there are a lot of other definitions, but we're normally looking at an electrically small antenna and trying to understand what's going on within that first quarter to half wavelength or so around a very electrically small antenna. So when you look at the radio spectrum, near-field wireless depends on you having a frequency low enough and a wavelength long enough to be able to close that near-field link at a reasonable distance. So if you're looking at some of the commercial systems, Wi-Fi operating at 2.4 gig or cell phone signals, the near field is so small that it's really not going to be a terribly practical technique. It's when you start getting down into the HF band, like around 13.6 megahertz, where there's an ISM band allocation, into the AM broadcast band, which is the frequency range that we at Q-Track work at, or down to low frequency RFID around 125 kilohertz, then the wavelengths start to get long enough for you to do some interesting things. Now, another property of the near field is it's a lot more complicated than the far field. Far field signals are characterized by two polarizations, horizontal and vertical polarization. And of course, you can measure the amplitude and the phase of those signals. That gives you 4 parameters that you could use in a modulation system or in a tracking system like Q-Track does. In a near-field system, though, you pick up an extra polarization. There's a longitudinal or radial polarization that's not present in the far field. And the electric and magnetic fields have not yet converged together to give you an electromagnetic wave. They retain independent characteristics and behavior. So you multiply that all out, and there are actually a dozen parameters of the near field that you could use either in a modulation scheme or as parameters for a tracking system. Now, a lot of these have been understood and known for a long time. In fact, you can go back to Heinrich Hertz's classic work on electric waves from the 1890s and see a chart showing how these phases progress, how electric and magnetic field phase vary from an antenna as you go out into the far field. This is one of the original parameters that Bob and I used in our near-field electromagnetic ranging systems. Individually, the electric and magnetic phases are kind of complicated. We would take the phase difference between them, which follows this relatively simple inverse cotangent formula, and by measuring that phase difference, be able to predict how far away the antenna is. Basically, measure how far along in that near field to far field transition we were, and use that as an estimate for range. Now, you also have to take a look at, another interesting parameter is the impedance of the near field. In the far field, the impedance is 376 ohms. That's basically the ratio between the electric and magnetic field strength in a far field signal always works out to 377 ohms. Well, that's not the case when you go into the near field. What you'll see is for an electric antenna, you have a lot more electric energy than you have magnetic energy. For a magnetic antenna, like a loop, you have more magnetic energy than electric. So you'll end up with either a larger or smaller impedance, depending on what kind of small antenna you're working with. It's interesting if you plot the impedance of a small antenna on a Smith chart. What you see here is in the top half of the Smith chart, I'm plotting the impedance of a loop antenna. It's an inductive impedance. On the bottom, I'm plotting what the impedance would look like for a small electric dipole, which effectively looks like a little capacitor. And the parameters there are showing what KR is, the wave number times the radius. So that's basically telling you how deep you are in the near field. And of course, in the limit, as you get many, many times KR away, this Smith chart is normalized to 376 ohms. So that's what the perfect match there corresponds to. But you can use another technique that was actually pioneered about the same time Philip Smith came up with the Smith chart. One of his contemporaries, Philip Carter at RCA, came up with an alternate version of the Smith chart. That's what you see these phase angle arcs are. What he realized is you could look at the phase angle associated with any spot on the Smith chart. And of course, that phase angle, the difference between the electric and magnetic fields, is effectively what you call the power factor for an AC signal. You know, when the voltage and the current are in phase with each other, you have real power transfer. When they are in quadrature, 90 degrees apart, which would correspond to the rim of the Smith chart, you have a purely reactive system with no net power transfer. And at 60 degrees, well, that's the magic phase angle where you have an equal mix of reactive and radiation, in this case, power transfer. So it's really interesting to plot this impedance of a small antenna on the Smith chart and see how that works out in terms of the efficiency. And of course, that phase angle in degrees is just the formula that Bob and I have been using to do location. Now, all of this work on near-field impedance is based on the assumption you're looking at a narrow band harmonic signal that's operating at a particular frequency. And I just wanted to, in this chart, point out that you get a somewhat different answer if you start looking at some interesting time domain applications of small antennas. Like, for instance, if you take this small dipole antenna, and which you can think of as a capacitor, and you short it out using a resistor, you get an exponential decay of the dipole. Basically, the time constant is equal to the product of the resistance and the capacitance. That's basic AC circuit theory. Well, if you take a look at the fields around it, what you find is that the current associated with that discharge is giving you an inductive magnetic field that's going in one direction, and the time derivative is in the opposite direction, which gives you a radiation magnetic field going in the opposite direction. And on a spherical surface whose radius is equal to the speed of light times the time constant, the magnetic field goes to 0. That's where those two components are equal to each other. And if you plot the energy flow, you note something very interesting, that all of the energy inside that sphere is collapsing back into the antenna. And the energy outside that sphere, the electrostatic energy originally associated with charging up that capacitor, that's actually the source of the radiation energy that is decoupling and moving away. And you can do an equivalent plot showing what the impedance is for either an electric or a magnetic dipole. Now, what I did to make it work and plot out on a normalized log plot is I took the absolute value, but inside the range of 1, where this is normalized to c tau. So that corresponds to the surface where the magnetic field is going to 0 for an electric dipole, so the impedance is becoming infinite, or the electric field is going to 0 for a magnetic dipole, so the impedance is 0. But inside there, the impedance is actually negative because it's associated with energy getting sucked back into the dipole. And it only becomes positive outside that surface when you have an outflow of energy. So this is it's a nice example to show very clearly how the fields around an antenna play a critical role in storing and releasing the energy from an antenna. In this somewhat contrived example, you can see that the energy that is radiated away is actually coming from the field stored around the antenna, not from the local antenna itself. So there are all kinds of interesting physics associated with how antennas work and how the near field works. One project I've been working on lately is taking a look at how superposition works and can give rise to a near field even arbitrarily far away from an antenna. For instance, if you imagine a constructive interference between two electric fields, now we know that that means you end up with twice the electric field. But we also know that the energy goes as the square of the field. So that would suggest that we have to have 4 times the electric energy. So if each wave had unit electric energy, you bring them together, they superimpose constructively, and somehow, through the magic of superposition, 1 plus 1 ends up equaling 4. And if you take a look at destructive interference, where the fields are pointed in an opposite direction, they're canceling out. The net field is 0, and you've got 1 plus 1 equaling 0. Well, what really happens is a very simple and elegant transformation between electric and magnetic energy. In the case of constructive interference of an electric field, if you take a look at how the Poynting vector has to work out there, the magnetic fields are destructively combining. At the same time, the electric fields are constructively combining. So yes, you do have 4 times the electric energy, but that's because you've lost all the magnetic energy and it's all converted into electric. And similarly, when you have a destructive interference and all of the electric energy vanishes, that's because it's converted into magnetic energy. So superposition and conservation of energy are actually compatible with each other, as you might expect. Okay, that is the end of the first half of what I wanted to talk with you about today. And again, if you have any questions, please feel free to interrupt. I have no problem with making this an interactive presentation and focusing on the things of most interest to you. Yeah, the question is, can you use that longitudinal or radial polarization in the near field to convey information? And the answer is yes, you can. In fact, I'll be showing you how, in fact, that is the best way to send information or signals in the near field when we take a look at the near field link laws. So good question. Are there any other questions while we're here before I go on? Okay, well, let me continue. What I want to do here is talk a little bit about how these very, very electrically small antennas, and when I say electrically small, I'm not talking about some huge lambda over 10 antenna. I'm talking about a minuscule 1/10,000th to 1/1,000,000th of a wavelength antenna. I'll talk about the links you have between antennas like this. And of course, the idea is the distance between the antennas is comparable or is much larger than the size of the antenna itself. Otherwise, things will get a lot more complicated and you have to do inductive coupling and more complicated calculations or figuring out what's going on. I'll talk a little bit about how you can use some of these principles to get a remarkably simple and straightforward formula to predict what the gain is of an electrically small antenna that you can then turn around and use in your near field link or in a far field link. I'll talk a little bit about how to calculate what the near field intensity is and some of the complications and pitfalls of the way that's regulated by the FCC. And time permitting, I might skip this. I'll go through NEC validation of some of the results of this. Whoop, wrong way. So to begin with, let's talk about these 2 gentlemen here, particularly the one sitting there at the desk. That's Harold Freese, and the formula that you see on the chalkboard behind him has been come to known as Freese's law. You can write it in typically 3 different ways. You can write it where you parameterize your antenna performance in gain. You can write it where you describe one antenna, typically a transmit antenna in terms of gain, and the receive antenna in terms of its aperture. Or you can write it like Freese did on the chalkboard behind him in terms of aperture. And incidentally, the gentleman sitting next to him is Sergei Shelkinov, who was a collaborator with Freese. And if you get the chance to read the book they wrote together on antenna theory and applications, it's one of the best antenna textbooks that I've read. So that's their formula. But of course, that assumes that you have antennas in the far field. All these formulas are assuming the 1/r² power transfer that you get in the far field. So the question is, what happens in the near field? Well, what happens is Freese's law will bifurcate. You get 2 different link laws, depending on whether you're looking at a like link or an unlike link. Now, by like link, I mean using magnetic antennas on both sides of your link or using electric antennas on both sides of your link. Now, an unlike link is one where you've got a magnetic antenna on one side and an electric on the other. And this is how it bifurcates. The leading term that you see here, the 1/kr², that's basically the normal far field everyday Freese's law that everyone who does RF engineering at least is accustomed to seeing. And you pick up these extra terms depending on whether you're looking at a like antenna link or an unlike antenna link. Now, this is the link I was alluding to. This is a radial polarization or longitudinal polarization link. If you remember how the patterns look for a loop antenna, you know that you'd normally expect a null on axis. So you'd be thinking it's null to null. In the near field, though, that is actually the strongest and best way to send near field signals, at least in free space, ignoring the propagation environment. But you'll notice there's no 1 over kr squared term in there. It of course, doesn't continue on out into the far field. Now, we can plot what those look like. Now, here is a plot of path gain in dB versus kr. And you'll recall that there's a lot of people talk about there being a free space path loss, as if somehow free space has this frequency-dependent attenuation associated with it. But really, that's just an artifact of the definition of using gain to describe both your transmit and your receive antennas. And I want to talk a little bit about that because it helps highlight and distinguish what's going on in the near field versus the far field. So the question is, what's the best way to describe an antenna? And I'll argue that gain is the parameter you probably want to use if you're describing a transmit antenna, but aperture really makes more sense for capturing receive behavior. If you look at ultra-wideband antennas, they help illustrate this point. A constant gain antenna ends up radiating a faithful copy of the voltage signal. So basically, the time dependence of the fields that are radiated is the same as the time dependence of the voltage signal that you apply. Now, of course, that's assuming that the frequency content is all in the bandwidth of the antenna, where it has that constant gain characteristic. On the other hand, if you want to receive a faithful copy of a signal, you don't want to use a constant gain antenna, you want to use a constant aperture antenna. If the aperture is constant on the antenna, then it will receive a faithful copy of the incident signal. And this goes back to a little appreciated asymmetry in what's called the law of reciprocity. One of the basic things that we all learn in school is reciprocity, that the transmit characteristics have to be the same as the receive characteristics. That's almost, but not quite, correct. And the way in which it differs is the transmit transfer function for an antenna is proportional to the time derivative of the receiving antenna transfer function. Now, in the frequency domain, it's a 90-degree phase shift, and you really have to be paying attention in a far-field link to be scratching your head over a 90-degree phase discrepancy between your transmitter and your receiver. So normally, that's completely ignored and not even noticed. But if you consider what happens when you move away from signals or fields and square them to look at how power or energy transfers, what that tells you is that the transmit power will be, we know that time derivative looks like multiplying by frequency when you move to the frequency domain. That time derivative is j omega. Well, when you square that, you get something proportional to omega squared. And what it tells you is that whatever you're using to describe your transmit antennas and your receive antennas and how they behave with a function of frequency, the transmit power is related to the receive power according to frequency squared. And of course, that's exactly the relationship that you have when you look at aperture versus gain. So really, gain is kind of a shorthand, easy way of describing the transmit power characteristics of an antenna, while aperture is really a handy shorthand way of describing an antenna's receive characteristics. Now, we've already noted in the case of that exponentially decaying dipole that energy gets stored in the near fields around an antenna before it's released. It gets pumped into the near fields and will hang around there for a quarter or a half period and then decouple and radiate away. And interestingly enough, that had been observed at least as early as Oliver Lodge in 1907. He noted that the effective source of electromagnetic radiation isn't at the oscillator or the antenna itself, but he described it as being about a quarter wavelength in advance of it. And he noted that Hertz found that also to be the case. That's looking at those phase plots that Hertz came up with. So this has actually been recognized for a long time. Now let's take that idea and run with it and see what that means for near-field links. So if we represent the transmit antenna in terms of gain and the receive antenna in terms of aperture, what we get is a nice, neat formula where the far field component ends up just being the 1 that you see in there. Everything goes as 4 pi over r squared as you let the signals expand on that the surface of a sphere of radius r. And then you still pick up these extra terms associated with the enhanced near-field performance of the link. There and there. So if we plot those and take a look, now we've effectively normalized out any frequency-dependent path loss that you would get in the far field, but we still retain some pretty significant path gain in the near field. What you see here is the L-pole and like links all go as about 60 dB per decade. And the unlike link goes as about 20 dB per decade there. So just as Fries's laws are really just the beginning of understanding how far-field propagation works, an ideal approximation that works in free space, things get a little more complicated when you start taking radio signals indoors and they have to work in the real world, in the presence of walls and ceilings and floors, and start bouncing around. So what we've done here is gather some propagation data in our facility. And what you see is one of our transmit tracking tags. It has 2 orthogonal magnetic antennas, one at the top and one at the bottom, that are fed in quadrature and generate a rotating field. Then we went to the blue squares around our facility and measured the signals, the electric and magnetic field strength, at the location of these gray boxes. Those are the receivers that we'd use in a tracking system. And taking a look at the dependence between range and signal strength, we'd normally expect like links to have an exponent of 1 over r to the 6th, and unlike to have an exponent of 1 over r to the 4th. What we actually saw is that the propagation was enhanced relative to what you'd see in a free space link. If you think about what's happening, we're working effectively between the plates of a parallel plate capacitor. The floor and the ceiling are ground planes that are confining the signals. So instead of the 1 over r to the 6th distribution of power we'd expect in a free space link, we're getting enhanced propagation as that energy is channeled into the 2D space between the floor and the ceiling. Interestingly enough, it ends up converging at on the order of about 1 over r to the 3rd or 1 over r to the 4th, kind of depending on where you go. And there's a lot of variation depending on where you are and the idiosyncrasies of the propagation channel. But interestingly enough, that's about the same way and the same kind of power law that you expect to see for far field links propagating in an indoor environment. Only far field links are being impacted negatively by multipath, and near field links are actually being enhanced by multipath. So we did a measurement to see what's happening on a detailed basis with respect to range, and effectively measuring the receive power, comparing it to our free space expectation of 1 over r to the 6th, starting at about 30 centimeters. And you can see it follows the trend line very nicely at 1 meter, out to 2 meters. By 3 meters, we're starting to get a little deviation. The slope is down to about 55 dB per decade. And by the time we hit 4 and 5 meters away, the slope is getting down to about 1 over r to the 5th. We're getting a 50 dB per decade roll-off. So what's happening there is the signals follow the free space behavior out to about the point where your range is getting comparable to the floor-to-ceiling height, and the signals are starting to get compressed and enhanced in the indoor propagation channel. So this is an example of what one of the signal strength plots looks like. So we have a receiver located here. The color scale is showing received power in dBm. And you can see that the power varies very monotonically and relatively slowly with respect to distance. Plus, the link is going almost all the way across our lab, which would be a distance of maybe 15, almost 20 meters. And just barely beginning to have a very low signal power around minus 125 dBm at the far side of our lab. So this shows you that the near-field links work very well in a cluttered environment. You'll notice they're going right through all of the plumbing in our restrooms, and of course all the steel stud walls and wires and so forth. So again, the advantages that near-field links have is they offer you modest data rate, really enhanced propagation. Typical ranges are going to be on the order of up to about a quarter wavelength. They're very robust in a cluttered environment, and if you need a robust, reliable link, they're characterized by no drops, no dead zones, and no fading. It pretty much works well until the point where the whole thing falls apart. You don't get little localized zones where you have rapid fading like you would with a short wavelength system. Now, I want to talk a little bit about antenna gain and some of the ways we measure antenna gain, and a really handy formula for understanding the gain of a electrically small antenna. Now, one of the techniques that's used in far-field wireless to measure antennas is the so-called 3-antenna gain measurement. You have 3 antennas, A, B, and C, and you measure the links between those 3 antennas. You can do the exact same thing at a short range with near-field or electrically small antennas by just using the 1 over r to the 6 behavior that you expect at very short ranges when you're in the quasi-static fields of the antennas. And in fact, when we did that on some calibrated lab antennas that we use for measurement by way of a double check of the technique, what we found is that our results, the average of our measurements of the 3 is this dotted black line here. They agreed very favorably with the manufacturer's specification, which is the red line running through the results. So within a dB or so, we're able to pretty accurately measure the gain of these antennas. And you'll also notice the kind of gain numbers that you get for these very small antennas would probably make a typical microwave wireless person's jaw drop, talking about minus 80 dBi gains. That's a very respectable gain for one of these small antennas. Because again, you have to realize it's on the order of 100,000th of a wavelength in dimension. The efficiency is measured in parts per billion, but because of the enhanced near-field link, antennas like that work very well in a near-field operation. And actually, that's also typical of what you'd see in the receive antenna for, say, an AM broadcast receiver. Typical gains are going to be on the order of minus 80, minus 75 dBi for a loop stick, a small loop stick antenna, up to maybe minus 60 dBi or so for a decent loop antenna. We've done some work, and in fact some of these results are due to a collaboration that Q-Track did with folks at the University of Massachusetts at Amherst, where we did individual measurements. We were able to get really good agreement measuring whip antennas, and we're off by a few dB measuring the performance and the gain of loop antennas. Of course, we took this technique and measured a lot of the different antennas we could get our hands on with different kinds of matching and so forth. And you can see our data over here. And we noticed something very interesting in taking a fine look at the gain data. What we noticed was that the gain of the antennas followed pretty closely within a couple, 3-4 dB of taking the product of the loaded Q with KR cubed. Now, it's been known since the time Wheeler pointed it out in the late 1940s that the performance of an electrically small antenna depends upon its volume, which of course is going to be proportional to KR cubed. That's basically the radius of the sphere occupied by the antenna. And of course, it makes sense that the efficiency of the antenna depends on the Q of the antenna. Effectively, the Q is telling you, roughly speaking, how many times that antenna will resonate before the energy that you have put into it will die out and be dissipated. So it's giving you the performance or gain of the antenna should be proportional to the Q. With ferrite-loaded antennas, we got similar results. Now, there's been an enormous amount of work on this question of what is the limit of the quality factor for an electrically small antenna. And I've just cited some of the more important and more recent results right here. But the thing to keep in mind is that the quality factor depends on the radiation resistance of the antenna, and of course these antennas are so small that's effectively negligible, as well as the loss of the antenna. And when you look at the efficiency of an antenna, you calculate it by taking the ratio of the radiation resistance to the total resistance. And if you relate that back to the quality factor, you can actually come up with an expression for the efficiency in terms of the size and the quality factor of the antenna. And of course, the gain of an antenna just depends on its directivity times that efficiency. Now, the directivity of one of these electrically small antennas is just 3/2. So when you multiply that all out, you get this expression right here, which in the limit of a very electrically small antenna gives you the loaded Q times that KR cubed parameter. And here we're assuming the antenna is well matched, so the unloaded Q is twice the loaded Q. So that's one derivation. A few years ago, actually just a couple years ago, Azad and his collaborators, I think at USC or UCLA out in Los Angeles, worked out a very handy link budget for inductively coupled resonant loops. And they did it the hard way, looking at ranges between the loops that were comparable to the size of the loops themselves. And they came up with a really remarkable relationship for the link law once you went to the limit where you separated your two loops by a distance substantially greater than the radius of the loops themselves. That's this result that's up here. And when you throw that back into the near-field link law that you expect at short ranges, which would be this formula right here, and solve for gain, you also get that same formula, that the gain of an electrically small antenna is equal to the product of the loaded Q times KR cubed. Now, if you've ever worked with electrically small antennas and tried to predict what the gain of a particular antenna is, you know it's a challenging job. Like with a ferrite-loaded antenna, there's any number of theoretical relationships governing the efficiency of your winding and what are the losses in your core and what is the strength of your coupling between, say, a pickup coil and the primary resonant coil itself. This makes it a matter of just winding something, measuring it on the Q meter, and seeing how big it is. So it makes it much, much easier to get at least a pretty decent engineering estimate for the gain of an electrically small antenna. And it also goes back to that same relationship I was pointing out in the near fields of a small dipole antenna, where if you look at that phase angle, the phase angle or power factor is telling you what the efficiency of the antenna is and what the ratio is of real power to reactive power. That also has that Kr cubed dependence associated with it. So when you take a look at what this means for practical applications, you'll notice in the Azad formula, there is no frequency dependence. The link law for electrically small antennas just depends on how big the antennas are and what's the Q you're able to get on both sides of the link. That's a really remarkable result. Basically says the choice of frequency depends on all the second order factors, like what is your regulatory scheme and what frequencies are you allowed to use, or what does your noise background look like, and of course what's the near field range. So effectively all near field links follow the same link law independent of frequency. And then what happens is you have a transition to far field behavior that depends on your frequency. If you have a high frequency with a short wavelength, that lambda over 2 pi transition will occur at a relatively short range. And as you go to a lower frequency with a longer wavelength, that near field to far field transition occurs at a relatively greater range. So in general, the small antenna gain is the product of the loaded Q and that factor, wave number times boundary sphere radius cubed, along with a constant that depends upon some of the details of the antenna structure. There are shape constants depending on how efficiently you're building your loop and what the ratio is between your loop length and your loop diameter. You have enhancements due to the ferrite loading. In doing the experiments, we found answers varying over about a factor of 2. We could simulate things using NEC, and NEC was telling us the constant had to equal 0.5. The theoretical calculations I was showing you indicated that the constant had to equal 1. And a lot of our measurements indicated that we seem to be doing better than that by a factor of maybe 2 to 4. So somewhere in that constant on the order of maybe 1/2 to 4 is where the gain ends up. But in any event, it's still a very good engineering approximation if you want to predict what the gain is for your small antenna. Now, the final topic I'm going to hit, and I think I'll just kind of gloss over this quickly, is how to calculate the fields around a small antenna. You can go to a great deal of trouble calculating what the field strength will be around your small near-field transmitter. And of course, we do that at Q-Track because we want to make all of our products have the exact same performance, and we want to make sure we're FCC compliant. But I've noticed even test labs end up with wildly more variation in their measurements of our transmit power than we know is in the transmit variation of the devices we submit for test. There are a couple of reasons for that I wanted to just run through quickly here. One is that the FCC's mandated testing procedure for electrically small antennas relies on an ANSI standard that in turn insists on you measuring the electric field strength from the device under test using a magnetic loop antenna at a range so short that the impedance is nowhere near 376 ohms, but you are required by law to assume it is 376 ohms and make all your calculations accordingly. And the end result is, if you're using a magnetic antenna-based transmitter, the electric field strength gets overestimated by about 10 dB. Now, if you really want to have an advantage, you could use an electric field transmitter that has comparatively weaker magnetic fields and get about a 10 dB kick above the limit. But it's interesting how the measurement techniques that are used for certifying these systems haven't quite caught up with the technology itself. Well, I will call it quits here and just go back and go through my conclusion. The famous American architect, Louis Sullivan, coined the principle of design or aesthetics that the form of a building or a device should follow its function. Form follows function, he taught. Well, in the context of wireless links, really the frequency you operate follows the function. Not all frequencies behave the same way. If you want a long-range, high data rate link, high frequencies are great. I mean, they are the frequencies you want to use in that kind of an application. But if you're looking at a short-range, robust link that needs to work well in a cluttered propagation environment, low frequencies really have their place. Low-frequency near-field links work very well for short-range links that are robust and only have modest data rate requirements. So I hope my talk has given you a starting point for understanding near-field wireless and how it works, some interesting features on electrically small antennas and their gains and their fields, and that this will be a starting point for understanding how near-field links can solve real-world problems. Thank you very much. I'll be happy to answer any other questions. The question is, how the heck can you have a path gain greater than 0 dB? We need to get out of the communications business and into the perpetual motion machine business, because that's suggesting that you can get more energy out than you put in. Well, it turns out, and I didn't really have time to go into it, there are other fundamental principles involved in that. Basically, the gain of your electrically small antenna cannot be so large as to violate conservation of energy. And I worked out about what that limit works out to in the context of the link law in the original paper where I looked at the link law, because that was one of the first questions I had. How the heck can I have plus 60 dB path gain for an RF link? And well, the reason is because the theoretical limit for the antenna performance is maybe minus 30 dB on each side of the antenna for an antenna that's smaller than the distance that's involved. It actually goes back to a very important and fundamental question in antenna theory, which is on the quality factor of an electrically small antenna. And it's known that the quality factor goes as 1 over kr cubed for a small antenna. The Q, or the quality factor, can't be higher than that. So basically, if you go back to that antenna gain formula, which is hiding here, if the quality factor is proportional to 1 over kr cubed, which is the limit for a very electrically small antenna, then that product of Q times kr cubed has to be of order unity. But in any event, that's a good question, and it's basically because there are other fundamental limits involved on the performance of your antenna. Any other questions? Yes, it's very monotonic and very slowly varying.
I know, long wavelengths are good for that type of thing, but what that's smooth, I thought.
Yeah, the question is just on the smoothness of the power in an indoor environment, and yeah, you'll notice it is very smooth. If you think about it, in a typical office environment, the delay spread that you'll see on your wireless data signals is on the order of maybe 4 to 15 nanoseconds or so. So let's say 10 nanoseconds of delay with the signals rattling around your environment. Well, if you're talking about signals arriving with various delays over that 10 nanoseconds, well, now consider what happens to a signal whose frequency is 1 megahertz. So the period of a 1 megahertz signal is going to be 1 microsecond. So a 10 nanosecond deviation is like a part per 100 difference. Well, that's 3.6 degrees of phase difference that you'd expect to see. So in fact, what we found when we first attempted to apply near-field electromagnetic ranging in an indoor environment was we were getting tracking accuracies on the order of that 10 to 20-foot type tracking accuracy. And we ended up applying an RF fingerprinting algorithm in order to do our tracking. So that lets us compensate for all of these relatively modest and monotonic perturbations that the propagation environment is imposing on the signals. But the wavelengths are so long, you can't get the two signals recombining 180 degrees out of phase and causing those kinds of fast fades and drops that you'd expect in a high frequency signal. And that's the real advantage and what makes near-field wireless so robust.
So how low have you seen it go in terms of near-field range?
Well, yeah, the question is if 1 megahertz is good, why not 1 kilohertz? I mean, how low can you go and still get the links to work? Well, what happens is that there are other parameters and other factors at play. And one of the really important ones is the noise in an indoor environment. The lower in frequency you go, the more noise you get. So the SNR gets worse and worse and worse and worse the lower in frequency you go. And 60 hertz would be a very bad place to try doing a near-field wireless link. So we found more or less empirically that AM broadcast band kinds of frequencies provided a good trade-off between having the noise low enough to be able to close the link and a wavelength long enough, like at a megahertz, the wavelength is 300 meters. And that's long enough to give you a pretty good, upwards of, maybe as far as 50-meter link if it's really, really quiet. Now, normally our links are anywhere from, 10 to 20 meters, but they're noise limited. And the noisier the environment, the closer to the 10-meter side you are. We've done experiments in very quiet environments, like in caves or in mines, where we're able to go out, 100 meters or more, though we're starting to get out into the far field by the time we get that far out. Any other questions? Well, then, thank you again for coming. I'd like to thank the IEEE Huntsville section and the sponsors for their gracious invitation to speak here. Thanks.